For the Exam 1 review, we're going to look at question 15. I'm going to use a template that I came up for Lagrange multipliers. I encourage you to maybe use this template as a way to work a problem or two, and then set the template aside maybe and do it on a blank sheet of paper. And then maybe while you're looking at the template, it does show you kind of the steps you have to go through. But eventually what you're going to want to be able to do is do these types of problems without the template at all, just on a blank sheet of paper. So that's what we'll work towards. So for using Lagrange multipliers, we're always given the objective function, and in this case it's given to us right here. So we're going to write that over here. So z f of x is equal to x times y. We're also given a constraint subject to condition, and this is 3x plus y equals 60. What we needed in the form of it being equal to 0, so we would subtract 60 from both sides. We get 3x plus y minus 60 equals 0. So this is our new function g of x, so we will go ahead and write that in here. And I got this equals 0 over here, so we remember this is equal to 0 as we go. Now it's the step of setting up the Lagrange multiplier function. So this function is something that's just given to us. So we take the f of x function, the objective function. We're going to subtract lambda for L, that's the Greek L, that's sort of the Lagrange multiplier, times g of x, 3x plus y minus 60. And this is where I have a little problem. Some of us, with this negative, we need to distribute through, so be very careful in this step. All we're going to do is rewrite it as xy minus 3 lambda x. So we kind of usually put numbers in front of letter constants and constants in front of variables. So we're going to rewrite this as minus 3 lambda x, and then minus and a plus make a minus lambda y, and then a minus and a minus make a plus 60 lambda. Okay, so now we have our lambda function, our Lagrange function set up. So this is kind of what we're going to focus on. That's what we have, that's what we're working with. And we're going to take the partial derivatives of the Lagrange function. Lagrange function. Lagrange. I'll have to maybe practice that a little bit more. So the derivative, the partial derivative with respect to x, we'll do that first. So xy, when we take the derivative of x, we get 1. The y is a constant, so we get 1y. We'll just write down y. The next term we come over to is negative 3 lambda x. You take the derivative of x, that's 1. So we get 1 times 3 lambda. We get minus 3 lambda. Derivative of negative lambda y, well, y is a constant, so is lambda. So that's a 0. And the derivative of 60 lambda, that's a constant, so that derivative is 0. You could have plus or minus 0, plus 0, but we're just going to take those off, right? So that's the derivative with the partial derivative with respect to x. Partial derivative with respect to y, and I guess there really isn't a lot of work to show. A lot of this we're doing mentally, but that's what's sort of expected when you take the derivative. Okay, come back to the same thing, but now y is our variable. Derivative of y is 1. 1 times x gives us x. Next term, we've got negative 3 lambda x. That's all a constant. X is a constant, so the derivative of this part is 0. Come to the third term, negative lambda y. The derivative of y is 1, so that's 1 times lambda minus lambda. And then finally, plus 60 lambda, the derivative of that term, it's all a constant, so that derivative is 0. Plus 0. Doesn't change anything, right? Becomes invisible. So now we're going to set each of these partial derivatives equal to 0. If you wanted to, you could do it up there, but I put a separate line for it because I want you to think, why are we doing this? It's because we want where these derivatives are not always 0, but we want to find where they are 0, because these are tangent lines, these are slopes of the tangent line. Where a slope of a tangent line is 0, we will have a maximum or a minimum. That's why we set it equal to 0. I see students sometimes solving, and it's just like randomly they start setting things equal to 0. We only do it for a particular reason, and the reason is because we want horizontal tangent lines that give us a minimum or maximum. Okay, enough of that. These lambdas I have a little problem with. Solve one of these equations for lambda and then substitute it into the other equation. So looking at this, I could use this one, but I'm going to have to divide by 3, so I'll get some kind of fraction, right? Solving for lambda, I would have to divide by negative 3. The second equation, that looks a little bit easier. I could just add lambda to both sides, and I get x equals lambda, right? Add lambda to both sides. So that's the one I'm going to use. Lambda equals x. So I've used this one to solve for lambda. What I'm going to do is then substitute into the other equation, which is this one here. We're going to put x in for lambda. So this becomes this part, y minus 3 lambda, right? But lambda is x, so this becomes y minus 3x. All right, and equals 0, right? This is the full equation. Y minus 3x equals 0. Okay, but still we've got x and y. We haven't gotten a number yet, but what we do now is we solve this new equation for x or y. Again, I think it's smoother if we just solve it for y. I could add 3x to both sides, and that gives me that y equals 3x, right? Add 3x both sides, you get 0 here, and you get 3x on the other side. Okay, we're in there. And then now we've got this third condition that has to be met. So these lambdas, partial derivatives have to be equal to 0, and g of x that we started with up here, this is also equal to 0. So what we do is we're going to substitute in for y, and we'll have an equation with one variable. So taking g of x, we've got 3x plus y, but y is 3x, so I'm going to plug in or substitute 3x in for y minus 60. Okay. After all of that, we are now ready. We can solve for the variable that we have there, right? And our variable is x, so we're going to do that first. Oh, we're plugging into g of x. This equals 0. It's not just an expression, it's an equation equal to 0. So otherwise we can't solve. So we get 6x, 3 plus 3 is 6, minus 60 equals 0. So let's solve for x. Add 60 to both sides. 6x equals 60. Divide both sides by 6. X equals 10. Very good. What can I do with this? Well, I can take this x equals 10. Now I can go back to this equation and substitute 10 for x, and I will be able to find y. Okay, so that's the next succession. Plug this back into the equation in part A. So I just labeled this A. I could have labeled it anything. And then solve for the second variable. So y must be 30. So we've done that part. The last step is then we're going to, now that we have both x and y, we're going to go back to the function, the objective function, the thing we want to maximize, and just we don't know otherwise except that this Lagrange process gives us a maximum or a minimum. And since we are looking in this case for a maximum, it will give us a maximum. It's kind of how we do this. So we want to find the z. So we're going to substitute in f of 10, 30 into the function x times y, 10 times 30, and that gives us 300. What is 300? 300, that is z. So we have our ordered triplet. X is 10, y is 30, and z is 300. And that's how we do Lagrange multipliers. I will put this template in with the exam review, and I'll put an announcement. Encourage you to either use it as I have, filling in the blanks, maybe once or twice. It's a method called underwriting. It's an ancient way of learning. You write underneath what the master wrote. Not that I'm the master so much, but the master teacher would kind of write something. You'd write directly underneath. You would underwrite that model, and through that you would learn. So this is underwriting. You may just pull it up on the screen and write it down on your own. That's fine too. But let me know how you find this. I can always adapt it, adjust it, but I kind of had this idea to do this about like 2 a.m. You know, those times when I wake up in the middle of the night and I think about math teaching. What can I do to help my students? That's what I do. So anyway, let me know. Hopefully it's helpful. Thank you.